Okay, in this video we are going to be talking about Rutherford diagrams and how to draw Rutherford diagrams. Now Rutherford diagrams are based, well, they're named after Ernest Rutherford. We have a video about him. And it's largely based around his idea of the atom, basically. He thought there was a nucleus in the middle, which is true. And he imagined electrons orbiting the nucleus, okay? And so in a Rutherford diagram, we imagine the electrons orbiting the nucleus. Now that's not actually what happens, but it's a very good representation of that. In reality, they're just spinning around randomly in random motion in sort of an electron cloud, okay? But they can be sort of approximated by shells, okay? This might be, if this is the nucleus, this might be shell 1, shell 2, shell 3, etc., etc. And these electrons, you can sort of imagine, are contained within these shells, similar to how in our solar system, the Earth is contained in the orbit around the sun. Right? We're not spinning into the sun, or we're not going out of orbit. We are contained in our orbit, similar to how the electrons are contained in the shells that they are in. Okay, so he imagined that there was a tiny nucleus in the middle, which he found out through the gold foil experiment, and there would be electrons from every increasing shell. And he imagined that as you went from a lower shell number, so let's say shell 1 to shell 3, shell 3 would have higher energy, so the electrons in shell 3 would have higher energy, and because of that, they would be more likely to be removed. Okay, so in the Rutherford model, you can sort of imagine as an inner nucleus, and you have electrons that are filled one by one, starting from the smallest shell to the largest shell, and you fill up electrons till you have the correct amount. Okay, so how do we draw Rutherford diagrams? Well, first you have the nucleus, okay? And oftentimes you will write the number of protons and neutrons in that said nucleus. And the number of protons will allow you to determine the element it is, okay? Let's use potassium as an example. Potassium, we see it has an atomic weight of 39, okay? And that means the number of protons plus the number of neutrons, okay? So basically, this means that we have 39 protons or neutrons, and 19 tells us the atomic number, which is the number of protons. So we know we have 19 protons, okay? Which is potassium, okay? And subtracting 19 from 39, we get 20. That's 20 neutrons, okay? You see from right here, because 39, the number of protons and neutrons have to add up to 39, okay? So we get 39 minus 19 is equal to 20 neutrons, okay? And that's what we write in the middle, the nucleus, okay? 19p plus, the plus here denotes that it's positive, and 20 neutrons, okay? And then we go about drawing our first shell. Now this potassium, because there is no charge, because it's not an ion, we know the electrons and protons have to be in equal amounts, okay? So that means if there was 19 protons, there has to be 19 electrons, okay? And the E standing for electrons. And the reason we know that is because potassium is neutral, right? So if we have 19 protons, then we have 19 plus charges, okay? We need to balance that out with 19 negative charges, and the only negative subatomic particle there is an electron. So we know we have to have 19 electrons as well, okay? So we know we need 19 electrons, and we begin filling each shell. Now remember, from the Rutherford model, the lowest shell, the shells closer to the nucleus, the lowest shell number, the lowest shells. So for example, this shell number 1, 2, 3, 4, the lowest shell has the lowest energy. That means it takes the least energy to add an electron. And because of that, electrons will just naturally tend to go into the first shell first, okay? And we know we need 19 electrons. So let's start adding the electrons. The first electron goes on the first shell, and we have room for more. This is 1 electron, so now we have 18 electrons left at this point. And at this point we have 17 electrons left at this point, okay? Now what's unique about the first shell is that the first shell only holds 2 electrons, okay? Each of these shells has a maximum number of electrons they can hold. And the first shell can only hold 2, okay? What about the second shell? Well, we filled up the first shell, okay? That's the lowest energy we could possibly put them in. So now we gotta jump up to the second lowest energy, which is the second shell. The second shell can hold 8 electrons, okay? So that's nice. 1, 2, 3, 4, 5, 6, 7, 8, okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We now have 10 electrons filled in, okay? Now we need 19, right? Because the number of electrons needs to equal the number of protons. So we need 19 electrons, but we filled in 10, okay? So we gotta keep on filling. We got the next shell. The next shell also fills 8, okay? So an important thing to know, aside from the first shell, every shell after that holds 8, okay? So we just 1, 2, 3, 4, 5, you get the point? So in this example, we have first shell holds 2, the second shell shows 1, 2, 3, 4, 5, 6, 7, 8, and so does the third shell. And by the time you get to the third shell, you have 2 plus 8 plus 8. 2 from the first shell, 8 from the second shell, and 8 from the third shell. And that leaves you with 18. But we need 1 more electron. Okay? So we put that on the fourth shell. Okay? Now it's important to realize that with the Rutherford diagrams, they go up to element 20. Okay, so they go up to the element with the atomic number 20, and that means calcium, okay? So anything below calcium, we can basically fill up 2, 8, 8, 8, and then so on and so forth. But after element 20, it begins to break down. The model begins to break down, and it's not so accurate. Because what actually ends up happening is electrons begin filling the lower energy levels again, okay? And that has to do, once again, with electron configurations, which we will cover a little bit later on in this course. But just understand at this point that Rutherford diagrams are good for elements with the atomic number 20 and below, okay? 20 and below, okay? Now, the number of electrons at the final shell is special. They are called valence electrons, okay? And these are most important because they determine chemical behavior. And right, once again, chemical behavior is really just talking about what it reacts with, just describes what it reacts with, and how vigorously it reacts, okay? Okay, you can sort of think of chemical behavior as that. What does it react with, and how vigorously, how likely is it to react, okay? So valence electrons will determine how likely it will react. And the valence is always at the final shell. You know, look, the shell number, the largest shell number. So this is 1, 2, 3, 4. We look at the electrons on shell 4, okay? And we see that we have 1 electron. So we have 1 valence electron. We will say that potassium has 1 valence electron. If, for example, it was calcium, calcium has atomic number of 20, okay? So we'd have 20 protons. Because it has 20 protons, we need 20 electrons to balance the charge. So we would have an extra electron here. And that would give us 2 valence electrons, because now we have 2 electrons on the outer shell of this atom, okay? Valence electrons. And a good, I guess, sort of thing to remember is that the closer an atom is to, well, actually no, I'll rephrase it like this. An atom wants a full valence shell. Okay, I'm being a little bit iffy with the definition here. But let's define what a full valence shell is. A full valence shell means a full octet. Okay, this is sometimes called a full octet. And a full octet just means 8 electrons in its valence shell. So, for example, if this was not potassium, okay, it was, I believe, what element is it? It's argon. Okay, let's say this was argon. Argon, because we only have 18 protons and not 19, we only need 18 electrons. And we know that from the first, when you add the first plus second plus third shell, you get 18 electrons, okay? So this would, so argon would have a valence shell of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 electrons, and that's a full octet. 8. Oct means 8, okay? So that's a full octet, and that's why argon is so stable, okay? Because it has a full octet. You know, every atom wants to be as stable as possible, and that's achieved when they have a full valence shell, a full octet. And you will notice, if we go to the periodic table here, argon is part of the noble gases. It's unreactive because it has a full octet. And all of these elements here have a full valence shell, okay? All of these, okay? And these elements, neon, argon, krypton, xenon, radon, and that element with a weird name has a full octet, okay? Because they are all noble gases, okay? These elements have temporary names, okay? You can see here that they're pretty newly discovered, okay? The septium and octium, okay? Helium has a full valence but not a full octet. I'll explain that shortly, but just understand that an atom with a full valence shell, a full octet, will be stable, and every atom wants to be stable. Okay, and full valence just means you have the maximum amount of electrons you can hold on that shell. So on the third shell, you can only hold 8 electrons. If you add one more electron, it goes to the next highest shell. So a full valence for an element that has valence electrons in the third shell would have to have 8 electrons, okay? Now if you were in the second shell, a full valence is only 2, because you have the first shell can only hold 2 electrons, okay? That also explains why potassium is so reactive, because potassium wants a full octet. It wants a full valence, okay? How can it get a full valence? If it can somehow remove this electron out of here, then it would have a full valence on the third shell, okay? Does that sort of make sense? Potassium's outermost shell, its valence shell, will have a full octet. Okay, 1, 2, 3, 4, 5, 6, 7, 8. If this lone electron leaves. And because of that, potassium is extremely reactive. And in that reaction, it will remove this electron. Okay. Let's see. Oh, and talking about helium. Okay, so I talked about how helium had a full valence and therefore very stable, but it did not have a full octet. Okay, if we drew helium's Lewis structure, helium, okay, it has 2 protons and 2 neutrons. Okay, look at it. Look at what happens when we try to fill. Okay, the first shell always have 2 electrons. Okay, so that's 1 electron. This is 2 electrons, right? And look, how many electrons do we need? We only need 2 electrons, right? To balance the positive 2 charge we have in the nucleus. +2 and -2, right? For a net of 0, a neutral atom, okay? We have 2 protons and 2 electrons. So we only need 2 electrons to fill. And look, they all fill up on the first shell. Okay, we don't need to go on to the second shell for a max of 8. We only need to go on to the first shell, which with a max of 2. Okay, and because the first shell can only sustain 2 electrons, helium has a full valence. Because, like I said, the first shell can only hold 2 electrons. Okay, so it is at max capacity. If you add another electron, it would go onto the third shell. Okay, if you made it lithium, it would go onto the third shell, but it's not. It's only on the first shell. Okay, so that's the key you want to remember. You want to understand that the outermost shell contains the valence electrons, and these determine the chemical properties. So how reactive it is, and what it reacts with when it comes to chemical reactions. The valence electrons are what determines the chemical properties. Okay, I'll show you in the next slide what. And this is the reason actually why elements in the same group, so elements in the same column, tend to have the same chemical properties. Okay. Finally, all atoms want to have a full valence. It's why potassium is so reactive, because it can easily lose one electron to get a full valence, a full octet in this case, because the third shell holds 8 electrons, and why it's so reactive. Yep. Okay, so let's go and draw some Rutherford diagrams. Okay, let's draw lithium. Lithium, we know it has 3 protons because it has an atomic number of 3 and atomic mass of 7. Okay, 7. Okay, so we have 4 neutrons. Okay, so let's draw them. We have 1, 2 in the first shell. The second shell, this is a pretty bad Rutherford. I think from now on I'm going to only draw the nucleus and the number of protons. 1, 2, 3. Okay, so look, lithium also has a valence electron count of 1. Okay, it has 1 valence electron. Let's do sodium. Sodium, 11 protons. Okay, so we have the first shell that can only hold 2. 1, 2. The second shell can hold 8. 1, 2, 3, 4, 5, 6, 7, 8. And finally the third shell, 8, 9, 10, 11. And the reason it's 11 is because we need 11 electrons to balance the 11 protons in the nucleus. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Oh, my bad. No, I did this wrong. And sodium 11 plus. Okay, so yeah, the first is 2, 1, 2, and we can fit another 8. So 1, 2, 3, 4, 5, 6, 7, 8. My mistake was I counted up to 8 on the second shell and then moved on to the third shell. No, that's not what you want to do. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then finally on the third shell you have 1. Okay, so look, sodium also has 1 valence electron. Okay, and we saw in the last previous slide that potassium has 1 valence electron, right? So over here, 1 valence electron. Okay, so far we're seeing that lithium, sodium, potassium all have 1 valence electron. And in fact, we can even do hydrogen. Okay, hydrogen has 1 proton, so 1 proton, and let's fill it up. Okay, we have 1 proton, therefore 1 electron, and boom. Okay, we have 1 valence. Okay, so what we see here is that all the elements in group 1 have 1 valence electron. And remember what I said, valence electrons determine the chemical properties of an element. Okay, and that's why all of these have similar chemical properties. That's why elements in a group have similar chemical properties, because they all have the same number of valence electrons. We could do this with beryllium. Okay, actually, yeah, let's do this with beryllium. Beryllium, it has 4 protons and 9 neutrons. Okay, let's see, do 1, 2, yada yada yada. Yeah, do the second shell, 1, 2. Okay, so now we have 2 valence electrons. Okay, 2 valence. Okay, notice how 2 valence electrons gives beryllium elements in group 2 a 2 plus charge, elements in group 1 a plus 1 charge, plus 2 charge. Okay, keep that in mind. Let's go with magnesium. It has 12 protons. Okay, so 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. Finally, 1, 2, for a total of 12. There's 10 on the first and second shell and 2 on the third shell. Okay, so 12. And once again, 2 valence electrons. Okay. Now, let's talk about Okay, now let's talk about reactivity, because we talked about how the alkali metals, group 1, is more reactive than alkaline earth metals. Okay, and the reason for that is because if you compare lithium, 3 protons, okay, this is lithium, the 3 protons, with beryllium, 4 protons, okay, 4 protons versus 3. Both of these want a full valence shell. In this case, it's not a full octet because their valence shell will only have two electrons. Okay, they want a full valence shell. Okay, and for lithium, the three proton element, it only needs to remove 1 electron, so it can remove it very easily. Beryllium, on the other hand, has 2 electrons on their valence shell that it needs to remove, so it needs to remove twice as much electrons, and that requires more energy. And because of that, beryllium is less reactive than lithium, because lithium can very easily give up 1 electron, whereas beryllium needs to give up not only 1 but 2 electrons. Okay, and you should also notice that in both of these cases, they're not trying to gain electrons, they're trying to remove electrons, because they can either lose 1 electron, lithium can either lose 1 electron or gain 7 electrons. And it's just math here, right? It's much easier to lose 1 than try to get 7. Same thing with beryllium, it's much easier to lose 2 than gain 6. Okay? It's also why these elements tend to be positive. Okay? Because when you look at lithium, the 3 plus, okay, it's going to lose an electron. And what happens then? Then you have 3 positive charges, but only 2 negative charges. Okay, the 2 negative charges come from the electrons in the inner shell. The 3 positive charges come from electrons. 3 positive charges come from the nucleus. It becomes you end up getting a +1 charge. Same with sodium. If you did this with sodium, you would have the exact same thing. You would have 11 protons, and you draw it 1, 2, 3, 4, 5, 6, 7, 8. And finally, the last one on the outer shell, you would lose one electron. The charge is unbalanced. You have a +11 charge and -10 charge, and that ends up with a net gain of +1 charge. This +1 charge explains why NaCl, sodium chloride, sodium has a +1 charge. Okay? Now we're done with the alkaline earth metals. Let's move on to the halogens. Okay, the halogens, let's use fluoride. Fluoride has 9 protons. Okay, so the first 2 shells filled. Second shell, you have 1, 2, 3, 4, 5, 6, 7. But look, 7 plus 2, that's 9. So we already balanced the charge. And once again, fluorine, like every other element, wants to get a full octet. It wants to get a full valence, okay? So it has 2 options. You could either lose 1, 2, 3, 4, 5, 6, 7 electrons. You could either lose 7 electrons like what sodium and beryllium did. They both lost electrons, or they can gain 1 electron, okay? And in fluorine's case, it's much more likely to gain 1 electron. Okay, it only needs to take in 1 electron than it is to remove all the 7 rest, okay? Because of that, fluorine will form a full octet and tends to be negative, right? Because it's, it's gaining an electron. So now you have 10 electron, 10 negative charge, and 9 positive charge. That equals to a net negative charge. That's why halogens tend to be negative. It's also why halogens tend to be extremely reactive, because it only needs to gain 1 electron, okay? Similar to how the alkali earth metals only need to lose 1 electron, okay? Both are really reactive for the same reason. They only require the exchange of 1 electron, whereas the alkaline earth metals, they have to lose 2 electrons, similar to the elements in group 16, they need to gain 2 electrons, okay? Awesome. Finally, let's do an example of helium. Helium has 2 protons. Okay, so it has a full valence, and that's why it's stable. That's why all these noble gases are stable, because they have a full valence. Let's look at neon. 10 protons. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. Okay? It has a full valence. It has a full octet. This valence shell has 8 valence electrons. Okay? And that's why these noble gases are, you know, quote unquote noble. They're unreactive because they have a full valence, a full octet. So just remember that an atom is stable when it has a full octet. Stable when it has a full octet. Okay. Now we're done with Rutherford diagrams. Let's go on to Lewis structures. Lewis structures are basically a simplified version of Rutherford diagrams. They only show the valence electron. So if we go back to our original example, the Rutherford diagram of potassium would look like this. Okay, it would look like this, and we have 1 valence electron. When we go to make the Lewis structure, we don't even show the number of protons. We just show the chemical symbol, the element symbol, and we draw 1 dot to represent 1 valence electron. We only draw the valence electron. This doesn't mean potassium only has 1 electron. It means it has 1 valence electron. Let's make calcium. Okay, calcium. Okay, over here, calcium over here, because it's an alkaline earth metal, it tends to form +2 ions. That's because it has 2 valence electrons, right? Calcium will tend to lose these 2 valence electrons, okay? And because it has 2 less electrons, the positive charge will overpower the negative charge and get a +2 charge, okay? And for something like chloride, okay, it's a halogen, so it will tend to form a negative ion. It will tend to gain an electron to get a full octet. If it needs to gain an electron to get a full octet, that means it must have started with 7 electrons. So we have 1, 2, 3, 4, 5, 6, 7. You show the valence electrons, okay? And what happens in, for example, sodium chloride in ionic bonding is sodium donates an electron to chloride. So chloride gets a full octet, 1, 2, 3, 4, 5, 6, 7, 8, a full valence shell. And sodium also gets a full valence shell. You know, sodium loses an electron, chloride gains an electron. It's the perfect deal. And chloride becomes negative, sodium becomes positive, and they stick to each other, and you have NaCl. Okay? Awesome. Now, it should be noted that when we have a positive ion, this is how we draw ions in Lewis structures. If it's positive, then it is a cation. Okay? So both, and if it's negative, it's an anion. You can remember it because an means, an sounds, you know, starts with an N, I guess. It feels like it starts with an N. So negative, anion, and this is a cation, okay? Both are ions, but anions are negatively charged, and cations are positively charged, okay? And remember, Lewis structures only show valence electrons. Okay, let's draw some Lewis structures. Let's draw magnesium. You draw the chemical symbol, and because it is in group 2, you have 2 valence electrons, okay? One cool tip, group 1 has 1 valence electron, group 2 has 2 valence electrons, group, you know, some people call this group 3 has 3, this has 4, 5, 6, 7, and 8, okay? So noble gases have 8 valence electrons, halogens have 7, yada yada yada, which is why you might see, you know, it's labeled as 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8. And it just skips the transition metals because it's a great way of showing how many valence electrons there are. Okay, so magnesium has 2 valence electrons. Let's do boron. Okay, boron, it's in group 1, 2, and 3. You know, 3A. Okay, or group 13. And because of that, it will have 3 valence electrons. You draw it like this. Let's do fluorine. It has group 1, 2, 3, 4, 5, 6, 7. 7 valence electron. 1, 2, 3, 4, 5, 6, 7. Okay. Let's do oxygen. It's in group 6 or group 16, and because of that, it has 6 valence electrons. And it's also why oxygen will tend to gain not 1 but 2 electrons. Okay, we'll gain 1 electron, another electron to get a full octet, to get a full valence. Okay, and that is essentially Lewis and Rutherford diagrams.